Introduction to CORScan Protocol on ARM Cortex-M3. In this course, we will see ARM Cortex-M3 MCU and Keil RealView software. Then we will see basic of automotive electronics. We will see basic input-output programs for ARM. Then we will implement these things with CAN protocol. We will use IR sensor, which can be used in collision avoidance system. We will use TV remote to demonstrate remote keyless entry. We will work with acceleration sensor to demonstrate vehicle speed control. We will understand and develop different automotive and embedded applications based on message transfer through CAN bus protocol, and many more things. Now the questions are, what is an embedded system? What are its characteristics? To answer these questions, let's start with the standard definitions of it. From the first point, it is very clear that the computer systems are general purpose and embedded systems are task-specific devices. In embedded system, softwares are commonly known as firmware, which is hidden inside the same hardware rather than in some other hardware. One of its most important characteristic is, it gives output within the time constraints, or you can say they are the time-bound systems. Let's understand these points by taking the example an air conditioner. To operate the AC, initially user intervention is required only to turn on and set the temperature. Afterwards, using its internal sensors, it detects the temperature, adjusts it, and even using the timer function, it can automatically turn off or on itself at certain intervals. So inside the AC, along with temperature sensor and other hardwares, a software program is embedded. In our daily life we are using lots of embedded devices, for example digital wristwatch, microwave oven, mobile phones, etc. It is a simple representation of an embedded system which contains the essential components. Basically, the input and output devices are nothing but sensors and actuators or motors. The CPU is basically a microcontroller in which inbuilt read-only memory or flash memory is commonly used to store the user programs or firmware. So it signifies the name embedded, which means software is hidden inside the hardware. These are the examples of some commonly used embedded systems: PDA, that is personal digital assistant, camera, cell phone, printer, television, GPS-based navigation system of automobiles, household appliances, etc. These points are self-explanatory, as we have already discussed about an AC which continuously monitors the change in temperature and adjusts it. This behavior is known as real-time and reactive. As the embedded systems are task-specific and to reduce the overall system cost, the designer has to smartly select application-specific processors rather than general-purpose processors. A hard real-time system, which is also known as an immediate real-time system, or reactive computing, or mission-critical system, is a hardware or software that must operate within the confines of a stringent deadline. The application may be considered to have failed if it does not complete its function within the allotted time span. Examples of hard real-time systems include ABS or anti-lock braking system, aircraft control systems, etc. Soft real-time system in which failure to meet a deadline is considered neither application nor system failure. It's just considered less good, thereby degrading the system's quality of service. Example: live audio-video systems and failure which results in degraded quality, but the system can continue to operate. As we have already discussed, the programs or softwares written for the embedded systems are known as firmware, and it lies within the same chip's read-only memory, or flash memory, and generally it may not require a disk drive. As an embedded system is a task-specific system, or performs only fewer dedicated tasks repeatedly throughout its lifetime, so the selection of hardware and writing of program is done once as per the requirement, and may not need to be programmed again and again. These are some high-end commonly used embedded systems, which needs high-end processing and processors. Da Vinci, telesurgical robot which performs open-heart surgery with a great accuracy. It uses a telemanipulator, which is a remote manipulator, that allows the surgeon to perform the normal hand movements associated with the surgery, while the robotic arms carry out those movements using end effectors to perform the actual surgery on the patient. One of the great advantage of using this method is that, the surgeon does have to be present, but can be anywhere in the world, leading to the impossibility for remote surgery. As per the figure, shown here, for the implementation of an embedded system one has to use these essential parts. Processing element, which is nothing but the processor or controller, performs the intended task by executing the user program. Hardware unit consists of the main circuit board and the associated circuitry like any specific ICs or any other arrangements for connecting analog devices or sensors etc. The peripheral system consists of the input-output devices like motors and sensors interfaced with the processing unit using different protocols. Then the memory unit, which is basically used to store the user program, intermediate results etc. Then you need to use different software for writing your program for the application and transferring the program into the chip. Generally cross-compilers are used for writing firmware for embedded systems. Here we are going to give a quick overview of the number systems used in the field of computers. If you are newbie in this field, then it will help you a lot in reducing the confusions during program writing. The base of a number system indicates the number of individual digits or symbols used in that number system. For example, in binary only zeros and ones are used, so its base is 2. Similarly, in octal number system from 0 to 7, 8 digits are used, hence its base is 8, and so on. Generally we peoples are using the decimal number system. Similarly, in computers only zeros and ones, that is binary number system, is used. 0 represents its false or low and 1 represents its true or high. This table shows the binary and hexadecimal equivalent of decimal numbers. Please notice that in hexadecimal from 10th to 15th is presented using A to F respectively. This is the writing style of the number systems with their base. Conversion between number systems is possible. If you want to convert a decimal number into hexadecimal, then it's easier to go via binary number system. Throughout this course we will be using binary and hexadecimal number systems. Here it is shown how to convert a binary number into hexadecimal and vice versa. In case of binary to hexadecimal, first you have to start grouping of 4 digits from the right, and if in the left you have only, let's say, 2 digits left, then you can add zeros in the left to make it a group of 4 digits. Now find out the equivalent hexadecimal value of each group. Similarly, to convert a hexadecimal value into binary, find out the 4-digit binary equivalent of each digit or symbol from the right. As in this course you are going to deal with a 32-bit processor, so at a time you have to calculate and find out the hexadecimal equivalent of 32 binary values or digits. For this, if you go for the conventional conversion method, it will take more time to calculate, so the 1248 method will help you. In the 1248 method, on the top of each binary digits first write down 1248 from the right hand side respectively. Then check the binary digits from the right side. Wherever you are getting a 1, take the corresponding value from the top. If you are getting a 0, then don't take anything for that. Now add all the values to get the equivalent hexadecimal value. Registers are the fundamental memory units present in a processor or controller. These are semiconductor memories and the fastest among all the memories present in a system. In the ARM Cortex-M3 microcontroller, all the registers are 32-bit registers. A user is allowed to write or change the contents in registers, but not in all the registers, because some registers are system-specific which can be read but can't be written. Now we will go through the details of the general purpose and commonly available processors or controllers of a system. Basically, either of a microprocessor or a microcontroller or the combination of both is used in most of the embedded systems. Now the questions are, what is a microprocessor and what is a microcontroller? Then where to use microprocessor and where to use microcontroller? To answer these questions we will go through. Generally, microprocessors are used in computer systems, which are general-purpose devices. So from the application point of view, we can say a microprocessor is a single LSI or VLSI electronic chip or IC, used in general-purpose devices like computers. As shown in the figure, in a microprocessor basically three major blocks are there, that is CPU, register and ALU. Registers are the temporary memory element which stores the intermediate results etc. CPU, that is central processing unit, which monitors all the activities going on the system and processes the user program and data. Then the ALU, that is arithmetic and logic unit, is used for performing the logical and arithmetical calculations or computations. Inside a microprocessor only the discussed three basic building blocks are present and all other peripherals like RAM, ROM, I/O ports etc. are outside of the chip but connected through the system's address bus and data bus. Similarly, in a microcontroller, along with the microprocessor's three primary blocks plus some other blocks are there, like input-output ports, timers, counters, RAM, ROM, ADC, DAC etc. That's why sometimes microcontrollers are also known as SoC, or System on Chip. So you can say a microcontroller is nothing but a complete microprocessor, plus some additional components, or peripherals, and, in some high-end microcontrollers you can interface different peripherals, which are used in a microprocessor. That's the reason ARM microcontrollers are called as processor rather than controller. For the normal working of a system, whatever the basic parts are required, everything is there inside a microcontroller in small quantity, and it may not need a motherboard. But in case of a microprocessor those things are outside of the chip, hence it needs a motherboard as used in computers. As per the previous discussion, microprocessor along with the motherboard and the CPU is standalone, but the single microcontroller chip itself is standalone. In case of a microprocessor, RAM, ROM is present outside of the chip, that is, in the motherboard, so it can be customized. But in case of a microcontroller, as all these things are internal, so you can't customize it, rather you have to change the whole chip or IC. Early microprocessors are used in applications where timing and accuracy is critical, like in airports, research centers etc. One should go for microcontrollers if constraints like cost, power, size is there. For example, in iPod, digital camera, mobile phone etc. Varieties of microcontrollers available in the market, so which one to select and use? To answer this question, you have to go through the details of the microcontroller classifications, which is based on the internal circuitry or devices known as integrated peripherals as well as its features. Here we will discuss the major peripherals of a controller. Let's start with the processor or controller core, that is whether it is 4-bit, 8-bit, 16-bit or 32-bit etc. The bit number specifies the data bus width or size. 8-bit microcontroller means, 8-bit data can travel on the data bus or it can process 8-bit data in a single machine instruction cycle. More the bit number, greater the speed you will get. Then comes the hardware architecture of the processor, like CISC, that is complex instruction set computer, or RISC, that is reduced instruction set computer, or von Neumann, or Harvard architecture. Each of these architectures having its own advantages and disadvantages. We will focus on some of these architectures later as the ARM Cortex-M3 is based on this architecture. Then comes the number of I/O ports. I/O ports are nothing but the gateways through which either your controller will get the data from input devices, like sensors, or it gives data to the output devices, like motors. It decides the number of input and output devices that can be connected with the controller, similar to the input and output ports of your computer. The next is clock frequency range. Clock pulses are known as heartbeat, required for every digital systems to function properly. It specifies at what rate the controller will process the data. Commonly used clock frequency ranges are 8 MHz, 12 MHz, 16 MHz etc. Nowadays in the modern controllers you will get number of advanced I/O interfaces, using which you can connect varieties of devices and modules in your project. The basic one is ADC, or analog to digital converter, as your controller is a digital device. it can directly process the analog quantities like sound, temperature etc., so you have to select a microcontroller which will have an inbuilt ADC feature. Similarly, DAC, that is digital to analog converter, does the opposite of ADC. If you want to do audio processing or want to produce different audio signals or tone using speaker, then you need this DAC feature in your processor or controller. Then the UART, that is Universal Asynchronous Receiver Transmitter, is a serial communication protocol, using which you can establish communication between PC and microcontroller, and make PC-controlled robot. The next one is SPI, stands for Serial Peripheral Interface, is also a communication protocol used to interface serial devices like SDMMC cards, CC2500 wireless transceiver module etc. Now the I2C, stands for Inter-Integrated Circuit, is a protocol using which you can interface devices like acceleration sensor, external EEPROM etc. Then comes CAN, stands for Controller Area Network, is a protocol widely used in automobiles for the communication between the numbers of controller present in a vehicle. ARM processors are widely used in automobiles for the implementation of CAN. I have discussed all these protocols briefly for the time. Later during the interfacing of different devices we will go through the details along with its timing diagram etc. Then you have to look for the different memory present in different controllers along with its size. The flash memory is used in pen drives, memory cards etc. is used in the controllers to store the user programs. EEPROM, that is electrically erasable programmable read-only memory, is used to store sensor data, motor data etc. Like in your PC, RAM is there, in microcontrollers also RAM is there. In microcontrollers often, SRAM, that is, static RAM, is generally used for high-speed registers, caches etc. because it's fast enough and consumes very low power. Then comes the power consumption. Different controller works at different voltage levels like 1.3 volts, 3.3 volts, 5 volts etc. As most of the embedded devices are powered using battery, so the power consumption of the microcontroller plays an important role. Special cares has to be taken while designing devices for space research and biomedical applications. Now we will discuss about some popular family or series of microcontrollers. The 8051 series microcontrollers, developed by Intel in 1980, was the first microcontroller. It's a Harvard architecture, single-chip, 8-bit microcontroller without inbuilt ADC and lack of advanced features. Nowadays different variants from various manufacturers are available including Philips, Atmel, etc. Example are AT89C51, AT89S52, P89V51RD2 etc. Then the AVR series, it's a modified Harvard architecture, 8-bit, RISC, single-chip microcontroller which was developed by Atmel in 1996. The AVR was one of the first microcontroller families to use on-chip flash memory for program storage, as opposed to one-time programmable ROM, EEPROM, or EEPROM, used by other microcontrollers at the time. Because of its advanced features and 32-bit variants, it is the one of the popular microcontroller series used by many peoples and industries nowadays. The main controller used in Arduino is also from the series. Atmel says that the name AVR is not an acronym and does not stand for anything in particular. The creators of the AVR give no definitive answer as to what the term AVR stands for. However, it is commonly accepted that AVR stands for AF, and VGIRDS, RISC processor, as per the name of the inventors, or Advanced Virtual RISC also. Example includes ATtiny13, ATmega8, etc. Then the PIC series, PIC stands for Peripheral Interface Controller, is a modified Harvard architecture for microchip technology. PICs are popular with both industrial developers and hobbyists due to their low cost, wide availability, large user base, extensive collection of application notes, 8-bit, 16-bit, and 32-bit variants. Examples are PIC16F887, PIC18F8722, etc. Now the MSP series. MSP stands for Mixed Signal Processing. That means it has both analog circuits ADC and digital circuits DAC to process analog signals as well as digital signals in the chip. It was developed by Texas Instruments in 1993. These are von Neumann, RISC-type, 16-bit, or 32-bit microcontrollers. These controllers are known as the ultra-low power microcontrollers. The current drawn in idle mode can be less than 1 microampere. It is designed for low cost and, specifically, low power consumption embedded applications. Examples are MSP430G2231, MSP430F5508, etc. Then the ARM series. ARM stands for Advanced RISC Machine. It describes a family of 32-bit and 64-bit computer processors designed in accordance with a RISC CPU design. Developed by British company ARM Holdings. ARM architecture has been in development since the 1980s, and is the most widely used 32-bit instruction set architecture. Nowadays ARM cores are more popular among all the available microcontrollers among the embedded developers and are used in a number of products, particularly PDAs in smartphones like the Microsoft Surface Tablet, Apple iPad, iPhone, Canon PowerShot A470, Akash Tablet of India, etc. ARM Limited does not manufacture or sell CPU devices based on its own designs, but rather licenses the processor architecture to interested parties like Apple, Atmel, Texas Instruments, Philips, and they are manufacturing the chips. Examples are LPC2138, ARM9, ARM Cortex-M3, etc. Now we will briefly discuss about different processor architectures. Princeton architecture is also known as von Neumann architecture. The basic difference between Princeton and Harvard architecture is based on the memory used for storing data and instruction. Princeton architecture uses a single memory or shared memory, that's why its memory structure and access method is simple, whereas Harvard architecture uses two separate or independent memory, that's why its memory structure and access method is complex. But simultaneous data and instruction access is faster than sequential access. Similarly, two separate or independent bus is required for Harvard architecture, which will increase the hardware cost as a single bus is required in case of Princeton architecture. Comparatively, the hardware cost is lesser. Now let's discuss the difference between RISC, that is reduced instruction set computer, and CISC, that is complex instruction set computer architecture. In case of RISC, the length of each instruction is fixed, usually 32-bit, and also only fewer formats of instructions are there, but in CISC the length of instructions are varying between 1 byte to 6 or 8 bytes, and also several format of instructions are there. In RISC, instruction operates directly on memory locations rather than memory values, as opposed to CISC. RISC architecture is also known as load store architecture, as the implementation is like load from memory into register, do operation on register, store register back into memory. In other words, only load and store operation access memory, and all other operations are registered to register. As registers are faster than all other form of memories, so it adds significant speed in case of RISC. As register involvement for processing is more in RISC, so it uses a large register bank compared to the register bank of CISC. As I have stated earlier, the instructions are equal in length in RISC, so prefetching and pipelining of instructions are possible, which is not possible in case of CISC. Later I will explain what is pipelining. Let's discuss another two important concepts related to architecture, that is memory mapped I/O and I/O mapped I/O. Memory mapped I/O is one where the processor and the I/O device share the same memory location and is accessed through the same memory-related instructions. The I/O devices are identified for communication through memory address, or the address of the port is stored in memory locations. I/O mapped I/O is also known as port mapped I/O. Processor and the I/O device have different memory located to each other, or uses a separate, dedicated address space and is accessed via a dedicated set of instructions. The I/O devices are mapped or identified using the port address. This is a common interview question: what is a big endian and what is a little endian system? Let's discuss it with an example. Let's say in a 8-bit system you want to store a hexadecimal data 0x4567. In big endian system the MSB part of the data that is 45 is getting stored in the lower memory location that is 0x5050, and the LSB part that is 67 is stored in the higher memory location that is 0x5051. Simply you can say the big endian system stores MSB part first then stores the LSB part. Similarly in little endian system the LSB part of the data that is 67 is getting stored in the lower memory location that is 0x5050, and the MSB part that is 45 is stored in the higher memory location that is 0x5051. Simply you can say the little endian system stores LSB part first then stores the MSB part. Now we will move for the details of ARM microcontrollers and architecture. As I have already mentioned earlier, ARM cores are used in billions of products, and ARM Limited does not manufacture or sell CPU devices based on its own designs, but rather licenses the processor architecture to interested parties like Apple, Atmel, Texas Instruments, Philips, and they are manufacturing the chips. The slide shows ARM partnership or association with various companies and products. The slide shows the evolution of ARM microcontrollers. In the beginning ARM was known as Acorn RISC Machine, later in 1990 it became Advanced RISC Machine. ARM became more popular for its ARM7 TDMI core which provides high code density and low power consumption. ARM7 TDMI specifies ARM7 plus Thumb plus Debug plus Multiplier plus IC. Thumb specifies support of 16-bit instruction set, Debug specifies it contains debug extensions, Multiplier specifies enhanced 32x8 multiplier relative to earlier ARM cores, and ICE that is in circuit emulator specifies embedded ICE macrocell which helps in debugging and reduces the work required by an external debugger. Now the question is why to go for ARM? Many answers are there for this question. The first one is, ARM is a RISC-type processor and RISC has lots of advantages over CISC so you will get more processing capability. Although it's a 32-bit controller but supports 16-bit as well as 8-bit data types. Programmatically little endian or big endian data alignment is possible. Its CISC-like functionality and RISC-type program implementation as well as reduced code length adds advantages over other controller. Supports to complex addressing modes-based instruction set is possible due to this RISC and CISC combined feature. Giselle technology is a combined hardware and software solution from ARM. It provides an extension to the RISC architecture, enabling ARM processors to execute Java bytecode directly in hardware and delivering unparalleled Java performance on the ARM architecture. So it will help the platform developers freedom to run Java applications alongside established OS, middleware and application code, all on a single processor. ARM is the most widely used processor core in the world due to its low power consumption and reasonable performance. Let's discuss the naming rules or conventions used in ARM processors. These naming rule is applicable up to ARM version 5. Then separate naming rules are used from ARM version 6M. The letters used in the version carry some special feature of the processor. For example, ARM7 TDMI specifies ARM Core version 4 or ARM Family 7, and TDMI that is it as Thumb decoder, JTAG debugger, fast multiplier and support for hardware debug. The slide shows the development details of ARM architecture version and its family with examples of some popular chips. As I told you earlier, separate naming rule is used from ARM version 6M onwards and in this course we are going to use ARM version 7, let's discuss it briefly. There are 3 extensions to ARM version 7 processors are available, those are version 7A known as application-oriented processors, version 7 are known as real-time processors and version 7M known as microcontrollers designed specifically for deep embedded use. The version 7A, 7R and 7M constitute the word ARM and are used in varieties of devices. ARM v7A, that is application-oriented processors, are the high-end processors running 1 GHz. Example: Cortex-A8, Cortex-A9 etc. are used in varieties of devices like mobile phones, iPods, tablets, computers, TV, GPS receivers etc. Then the ARM v7R, that is real-time processors, are the mid-range processors running 400-600 MHz. Example: ARM7 TDMI, Cortex-R4 etc. are used in varieties of devices like digital camera, hard disk drives, printers, automobiles etc. Similarly, the ARM v7M, that is microcontrollers, are the low-end processors running 200 MHz. Example: Cortex-M1, Cortex-M3 etc. are used in various devices like Bluetooth devices, speed control of motors, music players, game controllers, robots etc. In this course we are going to use a Philips ARM microcontroller, that is LPC1768, which belongs to ARM Cortex-M3 family and ARM v7M architecture.